we're going to study some of the internals of TempleOS. So first we're going to look at putting a bit pattern into the VGA memory. We're using in-out I/O port instructions to access the VGA registers, where it's got 4 bit planes, and we're telling it to write to all 4 at once. With this F right here means write to all 4. We're telling it we want the map register, and then we're setting the map register to F, which is all 4 bit planes. And then we're going to copy a 1010, a stripe pattern, into VGA memory, which starts at this is regular memory address space. We identity map, so it's an address is an address. Now we're telling it 640 by 480 and 8 pixels per byte. Then we're going to tell it to busy wait. That's just a for loop. We have there's no preemption, and so that will lock out the window manager. So what's going to happen is we're going to get a stripe pattern for 1 second. These are microseconds, so that's a million microseconds. That's 1 second. It's going to give a stripe pattern for a second, and then it's going to return control to the window manager. Okay, now we're back. So right now the VGA, there's a cache. VGA memory is slow, and so I only modify the actual physical hardware memory only when I have to. So it's only when something changes. So there's a way to flush the cache. It's Control Alt V. Okay, so right now the window manager is keeping track of the screen. So now we're going to do we're going to look at the 8x8 font. 8x8 is 64 pixels. So the font is 8x8. We're going to look at the font memory, which is for the character greater than. We're going to change it to this little bit pattern that I handcrafted. You have to look at the binary numbers and arrange them into a row by row. Anyway, then we're gonna sleep. This is different from busy wait. Sleep lets the window manager do its thing, and then we're gonna change it back to what we saved the original bit pattern. We can just use integers since it's 8x8 is just 64 bits. So here we go. So for 2 seconds, 2.5 seconds, it's gonna change the greater than everywhere on the system. You see that? I made a little. It's kind of like a man sideways. We can do that again if you want to see. Anyway, so it changes the font. That's what you did with the Commodore 64. So you don't really have to mess with character graphics. You can just use. It's not that slow. There's no reason for it. It's just fun. Anyway, so we're going to look at some disk blocks now. This is a drive report. My B drive is a RAM disk. My C drive is a hard disk with FAT32. Red C is the name of the file system that I created. So we're going to format the B drive. That's just to clear it out and get it reset so that it's perfectly fresh. We're going to format it with the Red C, which has 1 block per cluster. A cluster is the same as a block. We're going to get Microsoft and VMware and Linux to support the Red C when I command them with authority of God. Anyway, then we'll get rid of FAT, and then all we'll have is Red C. It's really nice. So we copied the home directory from my C master hard disk onto the B RAM disk. That's going to copy a directory tree. That's subdirectories as well. Then we're going to change directory to the home directory on the B drive. So there we copied, and now we're going to do an ordinary directory command, and then we're going to do a directory full, which is kind of like ls-l, except not really. So up here at the top is the regular directory. You can see it doesn't have the full date, and it doesn't have. This has clusters. So dot is the current directory, and dot is the parent. So what is this? This number right here, this is the cluster for the dump cluster. And then if you say, this is a utility cluster number, and then you can say write or the number in the chain. Anyway, so we want, the Red Sea is going to get rid of clusters, and we're not going to have a fat table. Well, anyway, I'll get to that. So here I'm going to dump. What is this? This is the Red Sea cluster for the current directory. These are 64-byte entries. It's supposed to be as simple as possible for kids. As a matter of fact, I think we even include, you're supposed to have a terminating 0 just to make it all the more easy. So you just copy this, you just copy a record, and it's you can copy it right off a disk. Anyway, so the first couple bytes are attributes. I think we have 16 bytes for attributes. You can have a fixed location block or fixed location file. We have a file name. We have a timestamp that's our native 64-bit timestamp that nobody else has. Anyway, so and then of course we have the block number of the start of the file, and it's a contiguous file. We also had a file size. I don't know where that is. Anyway, we can look at that if we really want to. dir entry. This is the start. Here we're using a 0 sized integer. You might wonder why we have a 0 sized integer. Well, that's so we can put a start and end of record. So you can use this label as a start, and then you do a bulk copy. We just copy this straight onto the disk. 16 bits of attribute, and the file name is up to 38. That's it, folks. No more. Cluster number is 64-bit, and size is 64-bit, and date time is 64-bit. What it is, the date time is 32 bits of date and 32 bits of time. So 24 hours is 32 bits, and so it turns out to be, I think, I forgot. If you want to find out, take 1.0 divided by 1 shift over 32, and I don't think that's right. Oh, of course. Okay, so let's do this. Let's start over. 1 shift over 32 bits divided by 24 hours divided by 60 minutes divided by 60 seconds. And this gives us, yeah, that's what I wanted. So we have a resolution of 49 thousandths of a second. And if you want to know date, we have the date is the upper 32 bits, so you can just add 1 and it advances 1 day. We don't have a structure with month, day, stuff like that. We just have a contiguous. So if we divide this by 365, we have around, so we can store, I don't know if this is correct, 11 million years before the next epoch. Anyway, so now we can also say dump block. Like I said, with this file system, a block is the same as a cluster. The main design criteria was simplicity, so that people can go in here. As a matter of fact, if we say dump with the true, we can modify. It's gonna write the block when we hit escape. So what we can do is come over here and let's just do blog. I'm modifying the directory block. Now if I hit escape, it writes it. Now if I do a directory, oh, I didn't hit escape. Okay, blog, budget, code, miss. So I modified the directory by hand. The police aren't too happy with people knowing what a disk block is, but God said it's our ancestral land, and they're just going to have to live with it. As a matter of fact, I want people to look at the Windows blocks, because you don't want ignorant people. That's evil. That's evil, keeping people ignorant. And then doing sting operations on poor, that's like just wolves eating children or something. I don't know. Anyway, so let's see what else we have here. Now we're going to look at the FS segment register. Okay, so we're turning on the compiler trace and we're entering an expression. You can use this as a calculator. 3 plus 4, 7. It simplifies the expression. The compiler simplifies constants, and then if we say I equals 3 plus I didn't initialize it, but I'm just showing you what the code is. So this compiles. These are in, well, 64-bit values added to a global variable. We don't have volatile. We never use register global variables. Local variables are register, but not global. Anyway, I just wanted to show that we have the compiler turned on, the compiler trace. If you do a directory, you can see what a directory command is. It pushes some strings. So some of this code gets freed if it's no longer needed. Otherwise, if you make a function, it stays around in memory. You eventually have to reboot, but we're trying to be a Commodore 64 that's not pathetic and it's modern, 64-bit. Anyway, so let's see what else we have here. Now we're going to look at the FS, is the FS segment register. This is you probably don't know assembly language, but there are registers, which are little things that hold values, and this is kind of I'm using it like a register. It used to be something different, but now it's been kind of it barely functions, and I made use of it, but most people can't make use of it. So I use it for the current task record. You see this number up here in the corner, 7FD9228. When I said FS, that printed a global variable. It's a register. It's kind of tricky how it actually did this, but anyway, you see that 228. You can see it's the same number. So we don't have process IDs. We have the address of a task record. The RIP is a register in the task record. We're going to look at the task record here in a second. We're going to turn off tracing, and we're going to do a man page on CTask. That's just anyway, CTask is a task record. So FS is a pointer to a task record, and you have the registers that get stored when you save the context. You have the current directory, current drive, and current directory. You have when you make an exception, it starts nestling the exceptions. It's tied in. The compiler is tied in with the everything's tied together. This task record, there's no separation. It's not really that big. There's a saying. Stalin said, "Quantity has a quality all its own." And if you keep it small, you can get away with You can get away with the pretty gnarly. This is kind of gnarly. It's kind of lots of different things. It's not that much though. It's pretty small. So now we're going to dump the memory, the size of the task record, FS. So this is the task record, and that's a static dump. This is static text. Now we're gonna do a document dump. This is getting into our. If you're familiar with TempleOS, you have the $sign is a special escape for document features. This is you can see it lit up and it's changing. This is a dynamic widget that that's a special thing. It's called a hex edit widget, It's refreshed 30 times a second when the screen's updated. This task doesn't change that often. Anyway, so now we're going to do a class rep, which is a dynamic. This is using the all the information and all the tasks and all the classes that you compile. The member variables are stored in memory, and some of these debug routines will automatically figure out what kind of class it is and what the member variables are. And this is dynamic, so you can see these changing off as we scroll around. This is the window coordinates of this task. On core 0 are your core 0 is where everything is done. The only reason the other cores are used is if they're slaves if you have a job for the slaves to do, then you do it explicitly. Otherwise, everything's on core 0. So if you run applications, they're on core 0, and then they create slaves on the other cores. So core 0 is the only. There's one window per task maximum, and one window per task. And watch this. I'm going to change the window. I just window left. I changed the I can change the window position. These are 8x8 grid positions. Anyway, so so one window per task. Only core 0 can have windows. The other slave tasks don't have windows. And applications are core 0. Anyway, so it's mostly for one application at a time. You can run more than one, but it doesn't have any kind of sharing for disks. So if one hogs the disk, that's it. It's instead of optimizing for a mainframe multi-user, we optimize for one user, where you only want to play one video game at a time. So we optimize for one video game at a time instead of. We try to keep the code simple, and so it doesn't do sharing. It's pretty. It will just. It will have poor sharing. It doesn't play nicely, but it doesn't really crash. It's pretty safe when it comes to locking down the heaps and devices and stuff. They're all safe. They just don't share. So now we're going to look at. We're going to change the current directory, which is a character pointer, in the task record. Then we're going to mallocate a fixed buffer. We don't do it like this normally. Normally we do a variable length. And then we're going to string copy demo games as a directory. We're going to copy that. So watch this. Look at that. We changed the directory by hand, which is a horrible abuse of power. But that's the power you have with this. As a matter of fact, if you want to access another task, interprocess communication is a joke. It's like there's nothing stopping you. So if you have if I have a variable here, i64i, and I say address of I, and then I come over here and I take this pointer address, and then I come over here and I say i64 star j equals 0x. So I just set a pointer. Now if I say star j equals 1, 2, 3, 4, 5, and then if I come over here and I say I just changed that variable. It's just a memory location. Anyway, so I can also say crosstalk, and then if I give the process ID, which is that's the address of the task record, so 0x 7fd fd 9a c28. I can tell it. This is I can put characters into his keyboard buffer. It's kind of a. There used to be there's a term for wires getting crossed. Anyway, so what I just did is I sent characters to his buffer. Anyway, we're going to do one more thing, I think, before we're done here. Let's see. Maybe we're done. Let's see. Yeah, we're done. Okay. So this is the Commodore 64 one of the major what it was used for was playing around and learning and poking and getting in and breaking stuff that was the fun. Instead of a video game, you just played around with this stuff, and that's our ancestral land. We have a divine right to this, like the Jews had a right to their homeland. We have a divine right to this low-level access. We're supposed to have access to ports and memory and disk blocks, and all of that is our divine right as Commodore 64 Americans and our descendants.